So I want to do the Haggard splittings, Haggard diagrams quickly again, but just a little more carefully. Say exactly how you get the Haggard error, just summarize that. But first, actually, let me give you another exercise. And this comes out of, Bruce will recognize this. Lots of things are coming out of my conversation with Bruce. Okay, so there's a little, so first I want to consider, it's going to be a function from the surface sigma, which I'll draw. It's just a torus with two circles taken out of it. To r, or to 0, 1. This is Morse function. And so this tells you what sigma is and what the function is. Okay, so there's this, and it's projected. It's the height function. I just embed this twice punctured torus into R3 and then project in the height direction. So it has this is a coordinate from a circle to a circle, and it has two curved points. I think that's one. And now I want to consider a certain automorphism of the torus, of the twice punctured torus. So to define that automorphism, here's one way to do it. If you so now define some phi from sigma to sigma, and that phi is going, well, so the way to describe this is first I can draw sigma like this. Okay, so what I'm doing is I'm gluing the opposite edges together, but I cut out a corner here, which those four corners piece together to make a circle, and then this is a circle here, right? And of course, I have to tell you how this sigma is identified with this sigma, right? And so I want to do it in such a way that there's various choices that I should make. So I think this following thing will characterize it. If I draw, I'll draw three curves here. A, B, and C. Those A, B, and C, I think I want them to be, so this is, so, if you imagine, well, you can think about how these identify. I claim you do it so that, let's say, this is A, this is B, and this is C. Now, what I want to do is the phi I'm going to define from this is just take this picture and rotate it 90 degrees. Okay. So, that's what phi is. But the point is, by drawing, it's hard to describe this diffeomorphism of sigma to itself in this picture. But here, there's this night I just rotated around the center, and it's clear that it extends boundary to boundary, right? Okay. Everyone understand this map I'm describing from the torus, twice punctured torus back to itself? And so then I want to consider. So phi goes from theta to itself, so I want to consider f composed of phi. That's another it's another Morse function from sigma to itself, sigma to 0, 1. Because this takes the boundary to the boundary, I guess I should tell you which. Let's say this is the bottom and the top. It doesn't much matter. You pick one of these, call it the bottom, or one call it the top, right? And so now the question is, fine. So these are two different. Now I have two different maps there from sigma, two different Morse functions of this coordinate, and I want to find a homotopy f sub t from f0, which is the original f, to f1, which is this f composed of phi. And keeping, which is constant on f inverse of 0 and f inverse of 1. Okay, so it doesn't move the top and the bottom, but it does something in the middle, right? And I want this to be, which is, I want f sub t to be Morse, let's say as much as possible. Okay, so this is a little bit open-ended. Maybe you can keep it to be a Morse function for all t, or maybe you can make it Morse for all but finitely many values of t. Maybe if those finitely many values are both cancel the critical points, right? And then I want, in particular, you're not going to write a formula for this, I don't think, but you're going to describe it somehow. This, what happens, maybe by pictures, and then so somehow to describe is find and describe, okay. And then draw. I'm going to just give you a word that a phrase called the surf graphic. You've already been thinking about this already, and I'm going to tell you the surf graphic for S of t. So the surf graphic is precisely this. It's you have it's going to be in the interval. It's going to be in interval cross interval. So 0 to 1, 0 to 1. This direction is t, right? And then this direction is the value of your function. So you just draw. It's just the image. This is the images of critical values in 0, 1 plus 0, 1, where this 0, 1 is t, and this 0, 1 is f sub t, the values of f sub t. So in other words, it starts out with two critical values. So your surf graph is going to start out. It's like it's the graph of the critical values, but of course there are things that start out like that. And if you think about it, it's going to end up like that too, because you're just composing with a diffeomorphism. And so you don't change. Diffeomorphism has no critical points. Phi itself is a diffeomorphism, so you're going to start and end with two critical values. And then who knows what happens here. Right? Where do the critical values do? Do they just go straight across? Do they cross 10 times? If there was a birth or a death of a canceling pair, for example, you might have something like this, that sort of thing. Maybe that's some ways that. And okay, but I mean, I partly want to emphasize the point that if I were just to draw a picture of this Morse function, it looks just like that Morse function. Okay, I mean, it's just also just going to look like this because I've just applied a diffeomorphism of the surface, and I'm still just going to look just like that, right? Except that what's really different is that here A and B are level sets of the Morse function. Okay, after I rotate it, then if I apply the rotation somehow precompose, for example, C might end up being a level set of the Morse function. So maybe it's going to look something like this. C is here, whereas A and B. So once if you have a submanifold, a particular manifold in mind, and there can be many different Morse functions on it that sort of up to diffeomorphism look the same, but are actually different. So that's sort of that's something that always hangs people up. Like things are the same up to diffeomorphism, but once you fix the manifold, then they're different. So I didn't say that very well, but this example is supposed to sort of drive home that point. Okay, now back to three manifolds and Hagar splittings. Hagar splitting, I want to emphasize there's sort of two different things, right? Hagar splittings and there's Hagar diagrams. And I want to describe both of those. And they're both ways to think about, a splitting is a way to decompose a given three manifold into two pieces. A Hagar diagram is a way to describe how to build a three manifold. Okay, that's the difference. So the splitting, first of all, remember, the splitting is sort of easier to understand initially. The splitting just says that you take your three-manifold, here's your three-manifold x3, you project it to R by a Morse function, F, you arrange, and this is something I still have to show you how to do, you arrange that there's a single index 0 critical point and a single index 3 critical point, and so this is index 0, index 3, and then a bunch of index 1 critical points and a bunch of index 2 critical points. These are index 1, these are index 2, and then you look at some regular value that's in between. You arrange the index 1s are all below the index 2s. You look at some regular value in between the index 1s and 2s, and then you take the inverse image of that regular value, and then that inverse image there is a surface. That's a surface that we call the Heegard surface. And the key thing is that it splits, the bottom half then is just a 0 handle and a bunch of 1 handles attached, so that's something completely standard. But then by taking the top half and turning it upside down, we see that it's also a 0 handle and a bunch of 1 handles. And by realizing that the genus of this surface is precisely the number of handles, we conclude that there has to be the same number of 1 handles here as there are 2 handles. Okay? And so therefore, what's below and what's above are both diffeomorphic to solid genus G handle bodies, where G is the number of these index 1 critical points, and therefore the 3-manifold can be abstractly viewed as decomposed into 2 genus G handle bodies glued together in some way. And so that's the Heegard splitting, which is sort of easier to say. So I think I wrote enough down about that last time. What I want to talk a little bit more about where the diagram comes from. But are there any questions about that? Okay. And one more thing to say is that, this depends. Initially, I actually drew these sort of suggestively as if all the index 1 critical points are at the same height, which sort of is not a generic phenomenon. And generically, they'd be, some would be a little higher, some would be a little lower. And then you might worry, what if one of the 1 handles comes down and is, in principle, you're supposed to do a single handle at a time. And then each handle is attached to the top of whatever you created by attaching the previous handle. And you might say, how do you know that you can actually, no, I'm sort of implying you can attach them all at once. And the point is, if this comes down and lands right on top of the pre-existing 1 handle, you can slide it off. Okay, so that's just the intuitive idea, which we'll make more precise in higher dimensions shortly. And then once you realize you can attach them all at the same time, you realize you could, if you want, sort of force all these index 1 critical points to have the same value. And so I will probably never reference it, but in the literature, you may see what's called a self-indexing Morse function. Especially 3-manifold people like to talk about these. And so the self-indexing Morse function is f from x to r such that for every critical point p, okay, the index of p is equal to the value of p. Okay, so that would mean that for it to be self-indexing, f of the index 0 critical point is 0. And f of the index 1 critical point is 1, f of all the index 2 critical points are 2, f of all the index 3 critical points are 3. Right? And that's just just a random convenience, but it presumes knowing that you can sort all the critical points by index, right? And that you can put all the ones of the same index at the same height. And then if you do this, then you can just, if the convenience is you just say that the Heegard surface, is f inverse of 3 halves, right? So sometimes you'll see people say that, right? That's because 3 halves is a regular value in between 2 and 3, in between 1 and 2. So people who, I like to think of a Morse function as being truly a generic object, and in that case, a self-indexing Morse function is not a Morse function. It's not generic. All right, but anyway, so the Haggard splitting, the Haggard diagram, we now know, so the Haggard diagram, we know that, let's call these two pieces A and B, A and B, and let's call this separating surface sigma, okay? We know that sigma is diffeomorphic to a standard. Sigma is an abstract surface embedded inside a three-manifold, but by classification of surfaces, we know it's a standard G surface. We just think of it as being a G surface. And what we're going to do is now, we made one argument by turning things upside down, where we took B, turned it upside down, so the index 2 became index 1s. And that allowed us to show that B was diffeomorphic to A. I'm going to do the opposite now. I'm going to take A and turn it upside down. So I want to think of, maybe the best way is let's fix standard genus G surface as a sigma sub G. Sigma sub G is somehow often, the land of Platonic ideals. There's these model surfaces floating around, and this is sigma 3, okay? And it's fixed canonical 1, and then sigma happens to be inside there. Yes?
So that would be the boundary of the F inverse of
no, sigma is actually F inverse of 3 halves. Okay. But it's the boundary of F inverse of 0 to 3 halves, and it's the boundary of F inverse of 3 halves to 3. Okay? And that's inside M. But I want to fix, so we fix a diffeomorphism phi from sigma G to sigma. Okay, and I'm going to draw a picture on this surface, okay? And which describes, which nails down the 3-manifold up to diffeomorphism. So then we look at, A and B as, well, I'm going to look at A, so here's sigma at the bottom, and then up here I'm going to do minus F, which has a bunch of index 2 critical points, and a single index 3 critical point, and that's A, and I have the same surface sigma, and I have, this is B, and it also, here I have the original function F. It has a bunch of index 2 critical points. And single index 3. Okay, so I look at A and B both as being cobordisms from sigma up to the empty set with these two Morse functions, right? And now that means that both A and B can be built by taking sigma and attaching a bunch of 2 handles, and then a single 3 handle. So, both A and B are built. Two handles. Well, the sigma across the interval. And then cap them off with the record. So if I draw the attaching maps for these 2 handles here, and I draw the attaching maps for the 2 handles here, and this is this fixed surface sigma, right? Then I've determined the 3-manifold. So another way to think about it is I can take the surface, thicken it up by a product, attach 2 handles here, and attach 2 handles from below, and then I cap off with a ball and a ball. And the point is now I can, those 2 handles are attached along, so 2 handles are attached along, or where they attach along, they're attached along, they're B2 cross B1s, attached along S1 cross B1s. B1s embedded in the surface, right? But as you mentioned earlier, and I owe you a more careful discussion of this, all I really need to draw, so I only need to draw the image of core S1 cross 0. Here. All the images of the S1 cross 0s. Because there's up to isotopy, it's sort of natural in the surface, there's only one way to thicken up a curve, right? To be an S1 cross B1.
Is that a codimension one?
That's a codimension one phenomenon. We can very shortly see that fail in one higher dimension, one higher codimension. Okay, but so therefore, so the upshot is, if I take, so therefore, if you take, what I want to do is consider this way. Therefore, you get G curves, let's call them A1 up to AG in sigma for the attaching, for the two handles from capital A. And you also get similarly get G curves called B1 up to alpha. I think that's standard alpha, that is the standard in the literature called alpha curves, beta curves, G curves, beta 1, and beta G. And it's also in sigma for the two handles from B. They're just where the, where I've got this fixed surface in there. But then what I really want to do is pull them, pull those back. Again, sigma is just this, it's sort of important to remember sigma is inside the three manifold already. If I want something that describes how to build the three manifold, I shouldn't use something that's in the three manifold. I should use some canonical object, right? So pull those back, pull back by phi to this actual canonical G's G surface sigma G, right? And then you get, this is what's called the Hagar diagram. Which is equals a collection of G alpha curves and G beta curves. I'm calling them curves, simple closed curves. In other words, embedded circles, okay? Beta curves in sigma G. And now you might want to spend some time thinking about, can you just draw any old curves and get a three manifold? I mean, so that's what you get out of it. Which curves actually work? Well, the point is that, let's think a little bit about that. Let's draw a picture, an example. One thing that is often done is one often chooses, so we use, okay, now, let's see. Blue is my free. So actually, I'll use blue for the alpha curves. And you can never know why that's consistent. Because that blue is the free region of the, if I got the one handle. So, well, you can think about why that's consistent with what I did. So I could do, for example, this, and this. And actually, if you think about it, if you actually saw this as a genus 3 handle body built by a 0 handle and 2 1 handles, 3 1 handles, right? Then the free regions of those 1 handles will precisely be thick enough neighborhoods of this. But those are the attaching regions for the 2 handles when you glue them upside down. So these are this might be alpha 1, alpha 2, and alpha 3. And then the betas could be all kinds of things. For example, beta 1, like that. I'm usually not very, I mean, if you prepare it right, you get other interesting ones, but I just go around. funny things can happen. That could go there, that could be beta 2, and maybe this could be beta 2.
So I have a silly question.
Yeah.
I've always seen alpha curves are red, beta curves are blue.
Oh, yeah, sorry.
So does that mean that,
It
that,
doesn't-
that sticking with your convention, which I understand and appreciate, does that mean like all the other, like when alpha's done in red and beta's done in blue, that those colors don't necessarily correspond to attaching in free, or?
Is the picture, maybe the picture just upside down?
So I think that if you just, I mean.
Or is it, yeah, I guess maybe.
So the
it's-
question is whether, so in
Which
some settings where you have to compute some invariants using these things, the question is whether if you switch all alphas with betas, right? If you just relabel the alphas as betas and the betas as alphas, whether you're, the worst case scenario, I can imagine that it corresponds to reversing the orientation of the manifold,
Okay.
conceivably. I don't know the Hagar 4, for example, well enough to know whether that works. So if you call blue red or red blue in Hagar 4 theory, I'm not sure. I suspect that doesn't change anything in the calculation, but it's possible it corresponds to replacing all your oriented manifolds with their reversed orientation. I don't think so. Or maybe like, there's spin C structures and running around that may switch, this one with it's an opposite of one or something like that. Okay, so for those who haven't heard of it, there's something called Hagar floor homology. Which computes invariance of 3 manifolds by think about the combinatorics of these curves on the surface. Okay. So the only thing to think about is if I just draw a random collection of curves, what do I have? Well, one thing to notice is, so observations are that the alpha curves are disjoint, are mutually disjoint, and the beta curves are mutually disjoint, just because they're attaching them, they can't overlap when they attach, right? They're mutually disjoint, and the beta curves are disjoint, but they can intersect each other.
They could have intersected, but then you would pull it off by hand or something.
No, they really couldn't intersect each other. I mean, you could have one running over. If a two-handle ran over the other two-handle, you wouldn't see its entire attaching map down in sigma, right? Because its attaching map wouldn't get down to sigma. So if it did run over, you'd sort of see it hit something and then disappear, right? And so then you just slide it off one way. But once you slid it all off down, so entirely lying in sigma, then they've got to be disjoint. Right? But the alphas can intersect the betas in all sorts of different ways. But then the other thing to observe is that what happens, so this is now when we talk about so how do we check, how do we know? Because suppose I draw a bunch of alpha curves and beta curves. I draw G alpha curves and G beta curves. G disjoint blue curves, G disjoint red curves on the surface. How do I know that actually corresponds to a closed 3 manifold and that I can actually cap each end off with a 3 manifold? And the answer is that after doing some operation to the surface called surgery, which I'm going to describe now, you should get a sphere, right? So how do we know if given collection alpha beta curves corresponds to a closed 3 manifold? Notice that you can always take a surface, and if you just draw G disjoint alpha curves, G disjoint beta curves, you can attach 2 handles above on the betas and below with the alphas and get a cobordism from some surface to some surface. And the question is that S2 going to S2? And I'll leave this for you. Well, so I'll talk about surgery in more detail in just a minute. So the answer is that you need that sigma minus the union of the alpha curves should equal a 2G punctured and same for beta. So what's going on there? Well, you can see it here with these alphas. What's going on is that if you attach, if you take this surface, a good way to think about, it's useful to think about the actual solid handle body that this bounds in R3, right? And if you're going inwards to the handle body, you attach a two handle along alpha 1, that means a thickened up disc along alpha 1, and a two handle along alpha 2, and a two handle along alpha 3, right? You've changed the boundary of the surface by cutting along here. And cutting, let me draw a picture. This picture, right? I want to visualize the inside of this as a bunch of two handles attached to that. Take this surface, thicken it up, right? Take this surface cross off, just draw a little thickening of it. Now attach a two handle, so that's just sort of a solid handle body with something drilled out. Now attach a two handle on the inside along alpha, so you attach a thickened up disc there, a thickened up disc there, and a thickened up disc there. Okay. And what's left to fill in is a ball. The reason it's a ball, the reason you can fill in a ball is that the new boundary is a 3-sphere, because what you've done is you've changed the boundary by taking, if you think about the new boundary of what you get, it's going to look just like what you had, except we now cut open each of those bits of genus. Once you fill in those solid thickened discs, the new boundary is like this. Or if you just thought about just cutting open, then the new boundary, this is precisely a 6-punctured S2. Okay? And this is equals S2. And therefore, when the operation of actually how the boundary changes when you attach a two-handle is you cut the surface along that curve, and then you get two boundary components and you cap them off the discs. So once you cap these off the disc, you have an ordinary S2, which you can then fill in with a handle, a three-handle. So that's all I want to say about A-bar diagrams for now. And I want to I keep enlarging the list of things that I owe you, and one of them is this discussion about surgery. Yes?
If you, well, maybe this is really a bad question, but if you think of these diagrams as, instead of starting with your three-manifold, you start with one of these diagrams and say it satisfies these conditions, then are these curves describing a automorphism of the surface? Or sort of like, they say it's like, how do I glue?
Yeah, they don't quite.
Okay, because there's not enough curve.
That's the subtlety, right? Exactly. That's exactly the subtlety.
Okay.
So that I sort of wanted to stay away from that.
Okay, so that was your comment.
That was my comment. That doesn't quite determine.
But up to isotopy, it does.
Well, no, it determines it up. It determines the three-manifold of the diffeomorphism. So the point is, you can if you take the, let's just take.
There's like Dane twists that don't matter.
There are Dane twists that don't matter because they extend across the solid handle body. Okay, so there's the if I take a surface that bounds a standard solid handle body, I can look at diffeomorphisms on the surface, modulo isotopy. That's the mapping class group. I can like diffeomorphisms on the surface, modulo isotopy, modulo the subgroup of diffeomorphisms of the surface that extend to diffeomorphisms of the solid handle plane. And those, then that's really what matters. And what this determines is the diffeomorphism of the surface modulo all those diffeomorphisms that extend
So
across
like the
solid.
kernel of that
Yeah.
doesn't matter.
Right.
Okay.
So let me just type in surgery. So surgery is the following. Surgery is what happens to some n minus one dimensional manifold, okay, if you attach a handle, an n dimensional handle to 0, 1 cross sector. Okay, so what I mean by that is, i.e., you get a cobordism from M to some new manifold M prime on the top, and M prime is produced from M in a certain way, okay, and so M prime equals the result of surgery. Actually, let me say it. K surgery, okay, is what happens if you, to this, if you attach an n-dimensional K handle, okay, and so you get a cobordism from M0 to M sun, and it equals the result of K surgery. K surgery apply, we say along, so let's, attach an n-dimensional K handle, yeah, well, so, let me say along the attachment. N-dimensional K surgery applies. So, the terminology is, you can do surgery along something. You're gonna apply surgery to a manifold along something. And the thing you would do surgery along, or the place you do surgery, is exactly the attaching manifold. So, I mean, just to be, so the point, I mean, to go back to the original two-dimensional picture, and a single two-dimensional picture. Okay, here's M, which in this case is a circle, right? And then I'm going to thicken that up, and then attach this handle, right? And I attach that handle. This is one handle, okay? And after I attach the handle, then I get a new manifold, which is two circles, okay? So this M prime equals S1 disjoint union S1. And so that is the result of, so we could say that S1 disjoint union S1 equals the result of surgery along what? Well, it's along a pair of points, right? Whatever I need to characterize the attaching map along an S0 as a result of one surgery along an S0 inside S1. Okay. Now, if I then said let's attach another handle, let's say disjoint union of two circles and attach a one handle, I could attach a one handle here, or I could attach the one handle here. And if I attach the one handle here, right, then I'll get a single circle. If I attach the one handle here, I'll get three circles. Okay, so depending on which way you do it, you can get different things. So in that case, you need to specify what embedding of the S0 you're looking at, whether you're embedding it as 2 points here or as 2 points here. Okay, so that does affect things. The example we were just looking at here is maybe an easier one to understand. So, so in general, right, what do you do? So how does how does the new boundary relate to the old boundary, right? Well, it's very simple actually. So if you loop, so if C is your attaching map from your SK minus 1 cross CN minus K into M is the attaching map. And M prime is equal to, well, you cut the image of the attaching map is no longer in the boundary. So it's covered up, it's buried down in the manifold, So the new boundary is that's no longer there, you've removed it from the boundary, and you've replaced it with the free part, the free region of the handle. So n prime equals n minus c of sk minus 1 cross b minus k, union, the other part of the boundary, bk cross s n minus k minus 1. Okay, now a lot of times when you say union, you should say union what, right? And actually it's precisely union, the gluing map is still just C, okay? Because C is a map, I'm sorry, yeah. C is not a map from this whole thing into anything, right? But C, I should maybe I have to put it this way, C restricted to sk minus 1 cross sn minus k minus 1. So I delete, but I want to be really, really careful, it's delete. Whenever I say delete something, I never delete something compact. Whenever I delete something, there's always boundary left. You either delete it and take the closure, or you delete the interior. Okay, that's what delete means, right? So then when I do that, I have I have a remaining boundary which is diffeomorphic to this thing by the map of C, and that's the little map I use. So in this case, for example, I won't write anything down. What are we doing? We're removing S1 cross B1 from the boundary and replacing it with B2 cross S0. B2 cross S0 is two disks, S1 cross B1 is an annulus. We remove an annulus, replace it with two disks, and that's what one surgery on the surface is. Okay. Zero surgery on the surface, for example, would be attaching a one handle. Zero surgery removes S0 cross B2, two disks, and replaces it with B1 cross S1. That's zero surgery on the surface. And now we'll talk about four manifolds and three manifold surgery. But another way to state this condition that I just erased is that the alpha and the beta curves should have the property that one surgery along the whole collection of alpha curves gives S2, and one surgery along the whole collection of beta curves gives S2. And that's precisely what you need. So surgery is what happens to the boundary when you attach the handle. So if you're ever going to cap something off, then the appropriate surgery is better produce a sphere. So you can cap it off with a top dimensional handle.
Is there some sort of easier in practice way of seeing that? I mean, is there like something you can say?
If I just give a bunch of curves and I want to see.
It's like condition in pi 1 or something.
I don't think so. Well, okay, yes. I mean, these are surfaces, right? You
Oh, you can just cut.
calculate the Euler characteristic and the number of boundary components.
You gotta
That's
get
it.
like
Okay, if two oriented surfaces have the same Euler characteristic and a number of boundary component, they're diffeomorphic. Same number of boundary components, they're diffeomorphic. So that's why surfaces are nice. Right? They're very amenable to computations because of that. This is the classification. So that would be what I would do if I was given some complicated mess of curves, right? I would try to find to do the Euler characteristic, I'd try to find one complex the thing retracts onto, or just compute by one or whatever. Just find a vertex and a bunch of edges that it retracts onto, and then the number of boundary components is precisely twice the number of curves, because each curve, when you open it up, is going to turn into two boundary components. So there's something that you can just say about the Euler characteristic of the complement of the collection of curves. Okay, so So the reason, this Haggard splitting way of drawing pictures, it involves drawing a picture on a surface, on an embedded surface. I started with a different way of just sort of flattening everything out, drawing things on the boundary of the zero handle. And I did that because that's the one that works. is going to work for us in four manifolds. Okay. So four manifolds, we look at the zero handle. Okay, that's B0 cross B4 now, so we have no hope of drawing already. Right? But its boundary is, so the boundary, which is the free region, we don't attach it to anything, we just poof, create it, and then building a four manifold. And then, but now we get, once we create a zero handle, then the boundary of it is equal to just, I'm just gonna say S3, right? And by stereographic projection, that's R3 equal to infinity. Let me ask you a quick question. How many of you have ever shown that stereographic projection takes circles to circles? Well, I never did it until 2 days ago. I don't know why I never did it, but
Maybe not the freedom.
yeah, the computations are identical to us.
Alright, okay.
It should be it's just all.
Start circle back in group. When,
Oh, we did.
when.
Oh, no, we did, okay.
Well, you did it in the
Then,
group.
yeah. Well, you do complex analysis, like one dimension.
Yeah.
Yeah, I don't know why I never did complex analysis.
Oh, that's true, you have to do it now.
So, alright. So now you just, so, and then again, we'll assume that all attaching maps except the final four handle are miss infinity. Okay, so then we draw all pictures inside R3. And then one handles is B1 cross B3. And now we can't draw the thing itself, but we can draw the attaching region is equal to S0 cross B3, which is just two balls. So inside R3, if I want, so I'll draw a sort of picture of it, I could draw again a ball and a ball. And I can say, ta-da, here's it. I've drawn. So this picture here is a four manifold with boundary. It's a zero handle, which has a boundary of just x3, and there is this space, ambient space, and then I've added the one handle to it. Okay. Now, there are various conventions because of the fact that we may have lots of one handles for whatever reason. Instead, with the three manifolds, I was labeling A and B and B and so on. In four manifolds, we tend to just put a dotted line between them. So typically you put a dotted line that indicates these are the same. So I could, for example, have two different one handles. Now again, there's I'm going to assume we're only building oriented four manifolds. And so if we're only building oriented four manifolds, then we don't have to state anything about just drawing the balls. I claim determines the embedding of S0 cross B3 up to isotopy. But now the two handles against one, so two handles. Yes.
But your spheres are codimension 2.
Those are balls, not spheres. 3.
Oh,
Okay.
okay.
These are
But their
solid
boundaries are
balls,
codimension,
right?
But their boundaries are codimension 2.
Right.
So that's not.
Well, okay,
Complicated.
it's really S zeros, right? And so it's really just about a point, something special about a point. And something special about one handle's not about, in any dimension, not about codimension. So the point is,
Well, I guess
if you want to
disconnect-
extend an embedding of a point to an embedding of a ball, right? Then I claim the only issue is which orientation I'm going to do it, right? And up to isotopy. Okay. So you just have to plot down a point and say if we fixed orientations, there's no ambiguity about how you extend that to an embedding of a ball. And I could just draw points, except that things may run over these, and I want. Okay?
But you don't have to worry about like knotting of spheres because you're
Exactly.
starting with points.
That's right, exactly, because these spheres are boundaries of balls, which are coming from points. These are S0 cross B3 is not.
And if they were knotted, that would be true.
Yeah, exactly. Although, yeah, exactly. The other thing is think about so what's the surgery that happens to so when I attach a zero handle, I just create a three-sphere boundary, right? So now what's zero surgery look like? What happens to the three-sphere boundary when I attach this? Well, again, we remove S0 cross B3, so these, these no longer, the interiors of these balls are no longer in the boundary of your formula. And instead, they're replaced by, you the free region then is B1 cross S2, which is just an integral across S2. So what you want to understand and imagine then is if you're walking along here, then you can hit this S2, and now there's an integral's worth of S2s that takes you out here. So this is like a wormhole.
Because going into the interior.
Well, no, going along the run, I've got this four manifold. So the analogy, this should be a direct analogy to this picture here, right? Okay, this is the boundary of the four manifold, which is what this whole three-dimensional picture is the boundary of the four manifold, right? I walk along, I hit this two-sphere boundary. Now, if I were to continue into the interior of the ball, I'd be diving into the interior of the four manifold. I'd be leaving the boundary. If I want to stay on the boundary, I can't go in there anymore. I have to go up and over, right? And I have to go take this S2 cross interval all the way across. Right? So, really, they're wormholes, right? You're traveling space here, you're there. And we're out of time for two handles, so let me just write down. Two handles are P2 cross P2, and the attaching region is S1 cross P2, solid torus. And you might be tempted, as we did with three manifolds, just to draw the S1. So can we just draw the image of S1 cross 0, the core of the solid torus, and be happy that that describes how this attaching map precisely? Well, the answer is no, because the point is you want to think about isotopy classes of embeddings of solid tori is a little bit different than isotopy classes of embeddings of circles, and it's precisely sort of an extension of this by Z, and precisely the issue is how much twisting there is as you go around the circle, and so that's framings of knots that we'll talk about next. So these are knots, these are framed knots.